Welcome back, students. So we were designing a beam and the initial calculations for the beam design has already done in the previous video. Let's recheck or recap the problem. A cantilever beam of length 4.5 meters supports a dead load of 18 kilonewtons per meter and a live load of 12 kilonewton per meter. Assume a bearing length of 100 mm, design the beam. So first we have to calculate the factored load, okay, using the dead load and live load values which is given in the problem. And based on this factored load, we had to calculate the maximum bending moment and the maximum shear force values. Now, next, what we were doing, we were calculating the plastic section modulus, which is required for our beam. Okay. And we had calculated this plastic section modulus using the formula for calculation of bending strength of beam, which is already given in the code. And I have discussed it in details in the previous video. Please check it. So, the plastic section modulus, which is required for our beam, was coming out to be as 2006.4 into 10 to the power 3 millimeter cube. So based on this value of plastic section modulus, we had to choose a section from either the handbook or the IS 800-2007 code, right? So the section which we had selected was ISLB 550 at the rate of 86.3 kg per meters. Okay, so while selecting a section, we should always keep in mind that the section which we are choosing should have a plastic section modulus value either equal to this or greater than this. Okay, so in this case, for ISLB 550, the plastic section modulus was 8.16 into 10 to the power 3 millimeter cube. All these specifications, this beam specifications are already given in the handbook as well as in the code, right? So the overall depth was 550 millimeter, the thickness of flange is 15 millimeter, the width of the flange was 190 millimeter, and the thickness of the web was 19 millimeter. Next, we had to classify the section. So there are 4 types of sections in which we can classify a beam. First class is the plastic section, then second class there is the compact section, then we have the semi-compact, and last we have the slender section. So whenever you are classifying the section, you have to make sure that your section is not a slender section, or it shouldn't be a slender one. Because why? A slender section has high probability of undergoing buckling or undergoing failure. So it should always be kept in mind that whichever section you are choosing, it should not become a slender section. Okay, it can be a plastic section or compact section, and in the worst case you can allow it to be a semi-compact section, but never should it be a slender section, right? For this, the classification of section, this portion is required. Okay, now today we are going to, in this video today we are going to calculate the design shear strength of the beam and the design bending strength of the beam, and we are going to also check whether the beam is in high shear or low shear. So first we will calculate the design shear strength of the beam. Okay, so the formula for calculating the design shear strength of beam is also given in the code. So we will find out where it is. Okay, so I have come to the code, clause number 8.4 of page 59 of IS 800-2007. So this clause is for shear. Let's read it. The factor design shear force V in a beam due to external action shall satisfy V being less than equal to VD, where VD is the design strength. So this is the value which you have to calculate. Now this value is equal to Vn, that is nominal shear strength, divided by gamma m0. So how to calculate the nominal shear resistance? The nominal plastic shear resistance under pure shear is given by Vn, which is equal to Vp, and Vp is equal to this, Av into Fyw divided by root over of 3. Av is what? It is the area under shear, and Fyw is the yield strength for the web. And you have to consider root over of 3 whenever you are including or whenever you are considering the area under shear, right? So you know the value of Fyw, it is equal to 250. Root over of 3 is there already. And Av, how to calculate Av? This value is also given in clause number 8.4.1.1. for hot rolled section. So our section was a plastic section and it also was a roll section. So we are taking the value of shear as this, that is equal to H into TW, where H is the overall depth of the section and TW is the thickness of the web, right? So AV is how much? H into TW. Let's go back to the problem. Okay, so AV we are calculating it to be D. Here capital D is equal to H. This is the overall depth of the beam. So AV is equal to D into TW, where the overall depth is 550 and TW thickness of web is 9.9. So this is coming out to be 5445, and you simply put these values in this equation. Okay, so AV into FYW divided by root over of 3 into gamma M0. Now if you calculate this value, it is coming out as 714.47 kilonewton. Okay, now you have to check whether the beam is in high shear or in low shear. Okay, so what do you have to do? In order to find whether the beam is in high shear or low shear, you have to compare the value of applied shear force with 0.6 times the design shear strength. Okay, you have to compare which values? You have to compare the applied shear force. How much was it? It is in the above. Okay, let's find out. Applied shear force. See, this is my applied shear force, which is equal to 202.5 kilonewton, right? So my applied shear force was coming out as is equal to 202.5 kilonewton. Clear? And what is my design shear strength? It is equal to 714.47 kilonewton. This is my design shear strength. So what you have to do in order to find whether your beam is in high or low shear, you have to compare this value of applied shear force with 0.6 times the design shear strength, GTH, that is VD. Okay, so this value is equal to how much? 0.6 into 714.47. 714.47. Okay, so this value is coming out as 428.6. Okay, this is equal to 428.6 kilonewton, right? Now this specification is also given in your IS code. I would ask you rather to look it up by yourself. Okay, so I'm keeping this part for you. So see, now if you compare these two values, then it is clear that the applied shear force is less than this value. Hence the beam is in low shear. Okay, now when this is the case, for this case, the design bending strength of beam has to be calculated according to the specifications in code. Let's find out. Let me clear all my writings and go back to my code. Okay, it's coming. So there it is. Go to page number 53, clause 8.2.1.2. Okay, so what does it say? When the factor design shear force does not exceed 0.6 times VD, where VD is the design shear strength of the cross section. See, our applied shear force or factored shear force, whatever it is not exceeding 0.6 times VD. In that case, the design bending strength MD should be calculated as beta B into ZP into Fy by gamma M0. Okay, this is the same equation which we had used to calculate the plastic section modulus. Okay, so again we are using the same formula to calculate the design bending strength, right? So now for plastic section, the value of beta B should be taken as 1. So we are putting 1 here into what is ZP? ZP was 222.8.16. This is already given in the handbook with respect to the section which you are choosing. Okay, into Fy value is 250. This is the yield strength of the beam divided by the partial safety factor, which was equal to 1.1. Now this value was coming out to be as 506.4 kilonewton meter. Now you again have to check the value of design bending strength with another value. This value is also given in the code. Okay, see, it is written, to avoid irreversible deformation under serviceability loads, MD shall be less than 1.2 times ZEFY by gamma M0 in case of simply supported, and it should be less than 1.5 ZEFY by gamma M0 in case of cantilever beam. So the beam under question here, or the beam that we are designing, is a cantilever beam. So the value of design bending strength which you have just calculated should be checked, and it should not exceed this value, 1.5 times ZEFY by gamma M0. So the this formula, when we put the values of ZE, Fy and gamma M0 in this expression, we are getting it as 659.045 kilonewton per meter. ZE is the elastic section modulus. Even this value is given in the code. Okay, so this value, the design bending strength, that is 506.4 kilonewton per kilonewton meter, is less than this expression, hence it is okay. So the beam is a low shear beam. Okay, and the design bending strength is also safe, it is okay. Now then you have to check for deflection. So in case of a cantilever beam, I think you have to, if you have forgotten calculation of deflection in structural steel, not in steel structure, in analysis of structures, for a cantilever beam, suppose this is a cantilever beam, right? And it was having UDL. Forgive my drawing, no, it's very bad. Okay, what would be my maximum deflection? My maximum deflection would be occurring, sorry, my maximum deflection would be occurring at the free end. So you also have to check whether my deflection which is occurring in this beam is safe or not. For that, for a cantilever beam which is subjected to UDL, this maximum value of deflection, that is at the free end, this value was WL to the power 4 by ATI. Okay, W is what? It is the factored load, factored UDL load acting on this beam, and L is the, L was this length. Okay, so you have to calculate the deflection using this formula, and you have to check with the value of allowable deflection. So the allowable deflection for a cantilever beam is L by 150. Okay, what is L? L is the total length, that is 4.5 meter or 4500 millimeter divided by 150. It is coming out to be as 30 mm. And the deflection which is occurring in my beam here is nothing but 40 point is WL to the power 4 by ATI. What is the value of elastic modulus for steel? It is 2 into 10 to the power 5, and the value of moment of inertia is already given in the code for the different beam specifications, so you can find it out from there. So you have to check this value of deflection with the allowable value of deflection and see whether it is safe or not, right? So I will end my video here, but I will request you to go to the subsequent videos where I will be checking the beam whether it is safe against buckling or not. Also I will check the beam against crippling. So till then, goodbye.